So welcome to the 51st Jansky Lecture. I'd like to introduce myself. I'm Tony Beasley from NRAO. This lecture series is a distinguished series established by the trustees of Associated Universities, Inc. and the National Radio Astronomy Observatory to recognise outstanding contributions to the advancement of radio astronomy. For those of you that don't know, the name of the lecture, Carl Jansky, is named after one of the pioneers of radio astronomy, and we welcome David Jansky, Carl's son, as we always do. So Carl Jansky was very important in our history. He founded radio astronomy and opened a new window onto the universe, and we'll hear a bit about that window tonight. Tonight's lecture is Gas and Galaxy Evolution by Dr. Jacqueline van Gorkom. Jacqueline received her PhD from the Kaptein Institute in Groningen, Holland. She was on the NRAO staff at the very large array in New Mexico for 8 years, rising from the rank of postdoctoral researcher to tenured scientist. I didn't hear that. She joined Columbia University, the Department of Astronomy, where she is a professor now and has served as chair of the astronomy department. And she has held visiting appointments at the Raman Research Institute in India, Princeton University, Caltech, Berkeley, and Kaptein. Her research interests are gas and galaxy evolution, which is the topic of the talk tonight, the morphology and kinematics of gas and galaxies in a wide range of environments. She's currently studying if and how these properties change with distance by observing the first neutral hydrogen deep field. And you'll probably be talking about that tonight, is that right?
I might talk about it.
Very good.
Yeah.
She's had many awards and honours, including the NSF Faculty Award for Women Scientists and Engineers and the Rutherford Chair at Columbia University. So we're delighted to have a scientist of Dr. Van Gorkom's stature for the Jansky Lecture, and please join me in welcoming her.
Okay, so I titled the talk Gas and Galaxy Evolution, but when I came to VLA in 1981, about 3 months after I had started taking data, and so after a few years I told everybody I want to make a neutral hydrogen image of the universe. And I was a little ambitious, but that is what I wanted to do. And so today I'm going to explain to you why I wanted to do that and how far I've got it, which is still a tiny fraction of the universe. So I've been a professor at Columbia for a long time, and I always take the students that work with the VLA to the VLA, because it's an amazing instrument, and I think they cannot do science with it without going to the telescope. So they do something back in return. So they always take beautiful pictures. And some of them, Jan, makes a beautiful quilt. Isn't that an amazing thing? So those are the kind of students that you like to have. This is really impressive. And it's the best thing about the Jansky announcement. You can see on the background this beautiful quilt. It's the VLA. Okay. Science. Everybody's impressed. This is also a nice picture, of course. Okay, so I want to give you a little bit more of a history. So in 1933, Jansky detected, or is it 32? 32, he detected for the first time radio waves from the center of the galaxy. So he could prove that there was actually radio emission coming from outside the Earth. That was a very important discovery. But then some history happened that actually is tightly related to the Netherlands, where I'm originally from. So first of all, what first happened was that Roter Reber, who was in Illinois, was an amateur, and he built his own telescope. And he started observing this radio emission much more carefully. And so he got beautiful contour plots. And then he was an amateur, and he thought, well, okay, I want to publish this. So he submitted it to the Astrophysical Journal. And so the Astrophysical Journal is a very serious journal, and they have referees who look at these papers and say, this is a piece of nothing, we won't accept this. And so the referees looked at this and he said, what is this radio emission from outside the Earth? We don't want this paper. But so fortunately, they had an editor, Chandrasekhar, who later got the Nobel Prize, who was much wiser than all these referees, and he said, no way, I'm going to publish this. So it was published. And so the good thing was that at that time, in Europe, there was this Second World War going on. And so in the Netherlands, there were a bunch of people, for example, Oort, who was a very good astronomer, didn't have much to do because he didn't want to collaborate with the Germans, so the university was closed. And he somehow read this paper, which was really great. So he got to hear about this radio emission from beyond the Earth. And so he immediately started thinking, he was a very clever guy, and he thought, it would be really nice if this radio emission had a spectral line from an element that we can observe, because radio wavelengths, he might then be able to look through the dust in the galaxy. So he recruited his graduate student, Van der Hulst, who had to hide for the Germans. So he was sitting in the basement during the war and had absolutely nothing to do. So he calculated what frequencies you could observe at radio wavelengths. And so what he predicted was that the neutral hydrogen band could be observed at radio wavelengths. And so that's what I've been doing for the most of my life. And so the interesting thing, all these people that I've mentioned have been Jansky lecturers. So Grote Reber was a Jansky lecturer in 1975. Oort was the second Jansky lecture in 1967. And it's the only lecture that was about neutral hydrogen. So 50 years later, you get another lecture on neutral hydrogen. And now I'll tell you a little bit about neutral hydrogen. So neutral hydrogen is an atom with a proton and an electron. And you can excite that electron to many different states. Here they are, higher energy states. But if you want to observe something at radio frequencies that's very low energy, you need a very low state. And so he figured out that actually at the ground level, you have this proton and this electron, and they're spinning in the same direction. And very rarely, the electron spontaneously starts spinning in the other direction. That happens about once every 10 million years. So you think, what is the deal about having a Jansky lecture about this every 50 years? Is way too often. But actually, no, it isn't. So the good thing is that galaxies have lots and lots of atoms of neutral hydrogen. So you can observe this line. And so that is what I'm going to talk about the gas in galaxies, neutral hydrogen, that emit line emission at 21 centimeters. It's just a radio wavelength. Okay, so now I'll come back to why would anybody want to make an image of a neutral hydrogen image? So neutral hydrogen is H1 of the universe. So to me, that sort of became clear in the 80s, why I wanted. And this is one of the images that really stimulated me. So this is an image made by John Hibbert, who was then a summer student at the VLA, and he later became a Jansky fellow and never left NRAO after that. But this image, what this shows is something pretty amazing. So here you see the optical galaxy. That's the light of the optical galaxy. It's about as big as our galaxy. It's a big galaxy. But the neutral hydrogen is huge. It's much more expanded. So this galaxy sits in a gigantic cloud of gas. And so during that time, we were wondering, so why does this galaxy have all this gas? Why do all the galaxies not have gas? So at that time, a big discussion was, could you look at a galaxy optically and predict what a neutral hydrogen would look like? And we couldn't. And you could do the same test. I did the opposite. Take a neutral hydrogen observation. Can you predict what kind of galaxy lives in that hydrogen? You also couldn't do that. So that was very interesting. So the first task was to sort of figure out why certain galaxies have certain amounts of gas. And so gas it's not only, so if you look at the universe where galaxies have this extent, it's very different from looking at an image of just stars, right? It's really different. But this gas is also important because almost all, certainly disk galaxies, have a lot of gas in their disk, and stars form out of that gas. So eventually, the gas in the disk affects the evolution of the galaxy. Right? If gas keeps falling in, the galaxy can continue to form stars. If you remove the gas, the galaxy stops forming stars and it dies. Okay, so that is why it is actually really important, not just for aesthetic reasons that you want to make an image of the universe. Okay, so now I was not the first to make an image of the universe. In fact, the theorists were way ahead. They have done it quite a while ago, and here it is. So this is a simulation. I will always say it very specifically when something is not real, it's just a simulation. It's made in a computer. But this is a simulation of the structure in the universe. It's a simulation made of the dark matter. So that is where most of the mass is. And basically, what these theorists show is that very early on, so high redshift is an indication of how early in the universe it is. So at a redshift of 18.3, that is very shortly after the Big Bang, you see here a very smooth distribution of the dark matter. And then if you come closer and closer in time, so here's 3.5, you see that this filamentary structure evolves. So you see filaments here, and in between you see big holes. And here, that is even more pronounced, and this is the present. So again, this is a simulation. But we can observe locally what the distribution is of galaxies, and they follow a very similar pattern. So we call this the cosmic web. It looks like a web, right? And so what I want to talk about today is how galaxies differ in different locations of the web and how they evolve. So here is a blow-up of, so this is now actually, they put galaxies in the simulation. It's still a simulation, but this is now the light and this is the dark matter. So what you see is that one of the very interesting things is that there is these enormous holes which are called voids, and they are about 90% of the volume in the local universe. There is huge spaces where there is nothing there. So today I'm first going to talk about galaxies that are in the very densest environments. So here you see it, where there is thousands of galaxies close together. Then I'm going to talk about very empty regions, which are voids. And then I'm going to talk about this experiment that I'm now doing with the VLA, where I am trying to look back in time, to look further back and see what is happening with the gas in the galaxy. And so if I live long enough, I might be able to make an image of the universe, but that might still take a while. Okay, so galaxies, just the light, actually is very different in different environments. And this is something astronomers have known for about a century. So they didn't really know about this cosmic web very well, but they knew that in low density environments, there were always lots of disk galaxies and very few round galaxies, ellipticals, right? And so if you go to, this is a group, this is something that would typically live in one of these filaments. See lots of disk galaxies. Now, if you go to a higher density environment, you start seeing that there are much more round galaxies, which are ellipticals, and S0s, which are basically spirals without much gas and no star formation. So if you look in the densest region, it's really amazing. There is 90% ellipticals and very few spirals, where everywhere else you see about 90% spirals and very few ellipticals. And so this is a very basic relation. It's called the density morphology relation. So here you see, this is the nearest cluster, beautiful picture. But so this relation, and here are the examples of these galaxies. So this is the ellipticals, they live in clusters. Here are the S0s, and then these are the spiral galaxies. Beautiful pictures, right? And so what I wanted to study is how does the gas in these galaxies, so take a given morphological type, how does it change if you go from one environment to another? Does the environment affect the gas? So this is the density morphology relation, and there's always been two sort of extreme points of view on how this comes about. The one extreme is that all these galaxies fall into the cluster and get affected by the environment. It is possible. I'm going to show you some examples. The other explanation is that galaxies that are formed in an already dense environment will be different from galaxies that are formed in a lower density environment. Equally well possible. So let me first show you. So this is what a galaxy would look like in a lower density environment. So a typical spiral has about 1.5 times the extent in the gas, which you see here, than in the stars, which is already a lot, but it's nothing like the first picture I showed you, right? So this is, but this could so be the standard for what galaxies look like in a lower density environment. Okay, so what can happen when galaxies fall into clusters? Now, this is not a simulation, it is a drawing by another student who also went on to become a Jansky Fellow, that's Ari Chun. So what she's drawing here is the stars in a galaxy, the cold gas, which is in blue. So this is the yellow is the color of the stars, the blue is the cold gas. And then in clusters of galaxies, there is actually very extended, extremely hot gas, like 100 million degrees. So there's very dense gas right in the centers of these clusters. And so here you're going to see what happens to galaxies when they fall into this cluster, where there is this hot gas and many other galaxies, thousands. So first of all, this seems very important. This galaxy falls in, and the ISM is really pushing against the cold gas. So the intercluster medium won't affect the stars, but it will push out the gas. And so what you see is, here's this cold gas. It's trapped out of the galaxy, and the outer parts of the disks simply have no gas left. That's one possibility. Another possibility is thermal evaporation. So you put this gas, this cold gas in that galaxy in this very hot surrounding, and the gas can actually simply evaporate and disappear. So in both cases, the gas will disappear and the galaxies will actually stop forming stars because they have no stars left. Now, another possibility is two galaxies encounter each other, they start interacting. And in that case, both the stars and the gas will be affected. The potential of the cluster can do something too. And this is another very popular scenario. So here the idea is that most spiral galaxies have during their life this reservoir of gas outside the galaxy, which is something by now we know that's probably true. And so when such a galaxy falls into the dense intercluster medium, that gas gets removed. So then it continues to form stars until it runs out of gas. So that's called starvation, very appropriately. And then there is something that was very popular for a while, which is called harassment, which basically means that if a galaxy travels through a cluster, it will get very fast distance encounters with thousands of galaxies. And each of these galaxies give a little pull. And so the cumulative effect of these little pulls really affects the morphology of the galaxy. So there is all these different possibilities, and now I'm going to show you the picture that Airy made with the VLA of the largest spirals in the Virgo cluster. So the Virgo cluster is the nearest cluster of galaxies, and what you see here is a picture of gas. And I'm actually going to show you lots of pictures of gas, and I just forget about the stars. So what you see here is, in the center, there is this very hot gas, 100 million degrees, so that is orange. And then you see in the outskirts, you see all the spiral galaxies that she mapped in neutral hydrogen. And just to make it visible, all these galaxies are blown up by a factor 10. And so what you see is that you immediately notice something. The disks in the outer parts are very, very large, and if you go to the center, they're very, very small. So that suggests the mechanism of ram pressure stripping, right? It removes the cold gas out of the outer parts of the disks, and this is a very convincing image, actually. I think it gives you the message. That's what's happening to the spirals. But there are some interesting things happening in the outer parts. But first, let me show you now I'll show you the stars and the gas. And so you see examples in the outer parts, where here are the stars, and the contours are the neutral hydrogen. There is way more neutral hydrogen very far out here also. Here is the galaxy, very extended neutral hydrogen. But so if you move in, you see here, this is the optical disk. So that's where the stars are. And you see that on one side, the gas and the contours have been removed. So again, the idea is that the galaxy falls into the hot gas and the cold gas gets removed. And this is one of my favorites. So this is a totally undisturbed stellar disk, and the gas seems to be currently pushed out. So it's happening right now. The gas is just pushed out of the disk. And here you see some examples where the gas is completely removed from the outer parts, and there's only a little bit left in the center. So this intercluster medium can have a big effect, and that's what I'm showing here. So another thing that we noticed here is if you looked at all the galaxies at a given distance from the cluster, they have these neutral hydrogen tails. These are little tails, actually. But if you look more careful, you see that all these tails are pointing away from the center of the cluster. So this suggests that these galaxies, they are falling in for the first time right now, and so the outer gas can get easily removed, and so it is pointing away from the center, you get these long tails. So this tells you that at about this distance from the cluster center, the gas is beginning to be removed from the galaxies. So that was an interesting result. Now there is this favorite galaxy of mine, which is NGC 4522, which is very strongly ramp pressure stripped, right? So it is stripped very deeply into the disk. So here again you see the H1 and the star. That's an amazing picture. You would never see that outside clusters. Now, this galaxy we have observed at many different wavelengths, and one of the interesting things you can do is you can actually look at the stars in the part of the disk where the gas has been removed. And so, as I said, gas is being used for stars to form out, right? So if you remove the gas, star formation stops. And so by looking at the age of the stars, which you can do with a spectrum like this, you know when star formation stopped. And so what this tells us is that it only stopped 100 million years ago, which means this galaxy is really, as the picture suggests, it's being stripped right now. Now, this is surprising in this case. I would not be surprised if this galaxy was in the center of the cluster, but it's very surprising in this case because this galaxy is in the far outskirts of the cluster, where there is very little ramp pressure, right? So there was a big puzzle for a while. This is sort of a Rosetta Stone for us on what happens to galaxy evolution in clusters of galaxies. So here is this is the contrast now at the X-ray, and this is the galaxy I was talking about. So you say, well, of course it could be stripped when it went through the center, but we can calculate how long it would take to go from the center all the way here, and it's at least 700 million years. So the stripping happened much later than that. So that was a big puzzle for a while, until we looked at a temperature map of the intercluster medium of this cluster. So that's what this shows. The different colors just tell you there is different temperatures. So in the center it's very, very hot, and actually yellow is even hotter. And our galaxy is somewhere here. So there is huge differences in temperature. And that suggests to us that there's a subcluster, a smaller group of galaxies falling into this cluster. The gas gets shocked, and because the intercluster medium starts moving, the ramp pressure goes up, and it's easier to strip the gas. So that tells us that it's not only any galaxy that goes through the center of the cluster, but also galaxies in the outer parts can get affected just by the way the cluster gets assembled. So a cluster grows by groups falling in. And so that is what we may be seeing here. So what I'm now going to show you is another simulation. I'm going to show you two simulations which were actually made by Greg Ryan, who is at Columbia, and both are showing gas. So the first simulation shows the formation of a cluster, and what you see is the temperature of the gas. And so here we go. Okay, I guess So if it is like yellow, it's very hot gas. If it is dark, it might be so cold that it is a galaxy. There it goes. So we are moving forward in time. So we start very early in the universe. And what you see is a cluster is forming here. And there are already some little galaxies in it. They are dark. And another cluster will be forming here. So there's two smaller clusters. And then something is falling in from here. It's all gas, but it's structural formation. And so at some point, these clumps start coming together. And then what you see is that the gas gets shock heated, and it moves out great distances. So this is much larger than the area of a cluster. And it affects the whole environment of the cluster. It's really, really neat. And so here you see the dark galaxies that are going through it. So we are almost, so this is the present time. So what you see is the cluster should be somewhere here. And so the temperature structure of the intercluster medium looks amazingly rich. It's a very complex structure, and it extends very far out. So this suggests that galaxies get affected as the cluster can assemble. And I think the astronomers here, I'd like to point out, there's also this cold gas falling in, which I think is at least as interesting. There's cold gas coming in along the filaments. Okay, so now I'm going to show you the next movie, which is higher resolution, and it doesn't show the temperature, but it actually shows you the density of the gas. So now white is high density, so the galaxies will be white. And so if you look carefully, there's a lot of things you can see, if it moves. There it goes. So you see the gas falling in, and so one of the interesting things is that as the galaxies fall in along the filaments here, you see that they interact, you get long tails. Some get stripped when they go through these filaments. And you see many have these long tails, which is gas that is being stripped out of the galaxies. Yeah, so we're almost there. So every poor galaxy that goes through the center loses all its gas, and it becomes an S0 galaxy. So the upshot of this is that we actually seem to understand cluster formation pretty well. The data and the simulations seem to agree pretty well. And this is, I think, one of the more interesting things, which I'm now really interested in, that if you look in the outer parts of the cluster, so you can see two things. In some cases, you see galaxies that are completely stripped, and that is probably because there's sloshing of the hot gas. But in other parts, you see these very long tails. This is hundreds of kiloparsecs of neutral hydrogen gas. And this is another one with neutral hydrogen gas, which I think is really related to these filaments, where there is already cold gas, which you saw in the movie. So you can see different things. You can actually probably see accretion of cold gas onto these clusters. What is more, in the outskirts of the cluster, there is actually an abundance of gas, which is really interesting, I think, for the astronomers in this audience who think about galaxies, if there are any. So now I'm going to exactly the opposite. I'm going to the most empty regions in the universe, which is voids, right? So many people think there's nothing in there, but actually there is something in there. So it's a very low density environment, not much happens. So you would think that galaxies grow very slowly. So let me remind you, so this is the pictures of the structure that the theorists predict. So the theorists can predict this very well for the dark matter. But how galaxy grows, they actually still don't know that well. And that is because it is a really complicated process. So until about 10 years ago, the standard picture was that you get this dark matter that sort of clumps in halos, and then gas falls in, it gets shock heated, becomes very hot, and then it very slowly cools, falls into a disk, and you form a galaxy. And then you grow the galaxy by merging with another galaxy, and another galaxy, and another galaxy. And that was sort of the standard picture for a long time. But then about 10 years ago, people started to realize that there was something wrong in that picture. And what was wrong in that picture is that very often this gas doesn't fall in from all directions, but it actually falls in along filaments, and it might not get shock heated to very high temperatures because the density is so high. So it might actually fall in right into the disk of the galaxy. And that's what's called cold mode accretion. Pretty obvious name. So there is two ways for galaxies to go. One of this is merging with smaller galaxies and this smooth accretion of cold gas. And so there have been now many simulations, and what they predict is that in the early universe, so high redshift, this is really early universe, this is the main way galaxies grow. So if you look at the blue curve, that is the contribution of cold mode accretion. And then so if you go to about redshifts of 1 and 2, this cold mode accretion becomes less important, and the halos become bigger, and so the gas more easily gets heated to high temperatures. So then you get this more smooth accretion. But if you go to the current time, you expect that in the lowest density regions and in the smallest galaxies, you still see this cold mode accretion. So of course, we wanted to look whether we could actually see that. So here is a study of galaxies in void. So voids are very, very empty, but they are not completely empty. And there was this very nice, let's see. There was this very nice all-sky survey, the Sloan Digital Sky Survey. And what you see here is slices through that. And the black dots are galaxies that really show that there is this beautiful cosmic web in a nearby universe, right? And so what we selected was the deepest underdensities in these empty regions and see if we could find a galaxy. And so the red dots, here you see a whole bunch, are in these deepest underdensities of the void. And so the next thing was to look, what does the gas look like in those galaxies? So here are pictures of these galaxies. Interestingly, they're all small. Most of them are star forming, they're blue, but we actually do see all morphological types. But most of them they're all really, really small, which is not a complete surprise. And this is now the neutral hydrogen of a sample of these galaxies. So what you see is quite the opposite of in clusters. In this case, you see small galaxies, that is the photograph, is the optical, that's the stars, and the contours is the neutral hydrogen. So all these galaxies have tremendously extended neutral hydrogen. Totally the opposite of what I was just discussing before. And actually it becomes even more interesting than this. So this was Catherine Krakal, who found this galaxy. It was the first galaxy she imaged in the void. Here you see this galaxy. It's a tiny galaxy. It's very regular, very thin, and it's rotating like this. And then if you look at the gas, it's rotating like this. It's perpendicular to the disk. So that is already very interesting. There is much more mass in the gas than in the stars. And what is even more interesting is in the disk, we've looked very deeply for any signs of stars. We've looked in the UV, where you can go really, really deep. There's nothing there. So this is a pure gas disk. And so we think this is actually a good example of this cold mode accretion. It's really accreting onto this galaxy. If it was just a merger with another galaxy, the inner galaxy would have been disturbed, and it's not. It would be totally messed up. So we think this is a very good example. And another example of interesting things happening in voids is that, so you actually expect that in a void, you again form this cosmic web. So you get very thin filaments, and then you expect that along these filaments, galaxies form. And so these are some examples. So here's one. So we were looking at this galaxy, and instead we found 3 galaxies along a very thin filament in neutral hydrogen, which again, we think is very interesting. Here's another case. So this is the neutral hydrogen, and there's 3 galaxies forming in there. So we think voids actually have these filaments where galaxies are still forming. Okay, and then we thought, well, okay, let's not only look at the Sloan Digital Sky Survey, but it turns out that we are actually sitting next to one of the biggest voids in the universe, which is also very interesting. And so it turns out that there are some galaxies in there too. This is one. So it's tiny. It has a hugely extended H1 envelope. And if you look at the regularity of the motions of that gas, which is indicated by these contours, then you see that there are real deviations here, which again we think might be evidence for infall. So voids are great places to actually look for evidence of gas infall into galaxies. That was the conclusion of this survey. So first of all, you find only galaxies that have a stellar mass that is smaller than our own Milky Way. They're all very, very small. And most of these galaxies are gas-rich. The kinematics is totally disturbed. And so other people have now, and we too, found that the gas is very metal poor, which is another indication that it might be pretty fresh primordial gas. Okay, so that's the void. And now I want to show you a picture. This is a terrible picture. It's hard to interpret, but I actually think this is the closest that people have come to making a neutral hydrogen image of the local universe. It's a very interesting picture. So what is done here is these authors, Dennis, Kilburn, and Korybalski, took a large part of the sky and they looked for all the galaxies, whether they had a lot of gas or not enough gas. So it is just the two extremes that I was discussing. Some galaxies are much more gas-rich than normal, and others are really much more gas-poor than normal. And so what is plotted here, so there's two slices in velocity, so let's look at this. So here, you can first look at this one. So if there's contours, it means the galaxy density is high. So this actually is the Virgo cluster. And so they plot if the galaxy is very gas-poor, it's red. So you see right in the Virgo cluster, it's very red. But then here, you see colors that actually indicate there's an excess of gas. So this says something about structure formation, right? It says that the gas is flowing towards these denser structures, and here you see them. And this is even more extreme, so this is further away. Here you see these very gas-poor galaxies, and here you see an excess of gas. Now to me, and that is again something for the astronomers to think about, this might explain this observation of galaxy conformity. What is this? If you look at a galaxy, which is star-forming, looks blue, and it has other galaxies around it, then these other galaxies are also star-forming. If you look at a galaxy that's not star-forming, a red galaxy, the smaller galaxies around it are not forming stars. And so the question has been for quite a while, well, why is that? And so I think it has to do with the large-scale distribution of the gas. So the star-forming galaxies are in these regions on the sky where there is a lot of extra gas. And that is why they are forming stars and the galaxies around them are forming stars. And if you go to another region, they're not. So this is something to think about, food for thought. But I think this is an amazing image. Poor quality, but an amazing image. Okay, so now I'm going to completely switch to a different topic, which is CHILLIS. So CHILLIS stands for the Cosmos H1 Large Extragalactic Survey, and I think last year there was a Jansky lecture on cosmos, right? Nick Scoville. Yeah, so this is actually now looking at the cosmos field and doing neutral hydrogen observations. So this is a project that's now done with the Jansky VLA. It has become possible because the VLA got upgraded. And it is 1,000 hours of observing time, which eventually we will get. So we started a few years ago, and it goes a little slow, but we are getting there. And so what is interesting about this survey is that for the first time, we can now actually look back in time and probe deeply what the gas does to galaxies if you look earlier in the universe. So that's the goal, really, of this project. And it's not only that, it is also, the JVLA has now become a pathfinder for a new telescope that will be built maybe in about 10 years, the Square Kilometer Array, which will be an amazing telescope. And so this is the first time that you can sort of do this kind of science already that will eventually be possible with SKA. And so in many different countries, people are building smaller telescopes that are prototypes for this SKA, and they're called the Pathfinders. And in this collaboration, it's a huge collaboration, we have collected people from all these prototypes. So the only thing that is important about this picture is on top you see Happy Hour in Socorro. It's where we go to do our observations. But what you see here is all these different colors. And this tells you that there are people from 6 continents collaborating on this work. So it is a great collaboration, and we are just teaching each other what you can do with this kind of data. Because it's not completely trivial what we are trying to do. So here we go. So what is unique about the Very Large Array compared to these other pathfinders that are being built? It's actually the first strength is that it's up and running. Amazing. These other telescopes are still being built, but they get there. And actually, it is more, the sensitivity is comparable to the most sensitive pathfinder that will be built. But the weakness is, these pathfinders are all survey telescopes, so they will just do surveys. They do one big project at a time and they observe forever. While the VLA is an amazing telescope. Anybody can write a proposal and get time, which is really, really nice. But so you're competing with many, many other users, and they don't just want to stop everything else and do a survey, even if you say that it's really important. So that's the drawback. Okay, so the science motivation, I think you now understand. So it's basically we want to see what the gas does to the galaxies and look at the location of the galaxies, for what that word. So is it true that if you go to higher redshifts, like redshift 0.5, does this accretion become more dominant? Because that is actually what the theorists predict. So that is really the main motivation. And so what do we know about observations? I've been showing you simulations, but we know a few real facts. One is that the star formation between redshift of 2 and 0 drops, so this is the rate of star formation in the universe, it drops spectacularly to the current time. So for some reason, the star formation stops. Now, we don't really know why that is, and so quite likely it has to do with the gas in the galaxies. So what we do not know at all is what the gas is doing. So what you see here is, this is actually a ridiculous plot, this shows the gas as function again of look-back time or redshift here. So this is sort of the beginning of the universe. And you see these different points, and those have small error bars. These points are pretty well determined. And then here there is this huge gap where people really don't know much of at all. And there is huge uncertainties. And then at redshift 0 in the local universe, we know it really well. So there are very small error bars. But so, of course, this is the data. They're very honest. We don't know much between, say, a redshift of 0.2 and 1. It's totally unknown. But the theorists are really doing a very poor job. So despite the fact that there is gigantic error bars, they predict that it should be like this. So they cannot even go through these gigantic error bars. So I think it's just time to get data, and that's what we are doing. So what do we know about H1 as function of redshift? So this basically summarizes. Here is redshift. So it goes from 0.05 to about 0.25 in this plot. And this is again a slice of the Sloan Digital Sky Survey. So you see the structure of the cosmic web. So this area is very well probed in neutron hydrogen. That's done with the Arecibo telescope. It's called the Alfalfa survey. It's a fantastic survey. They've done the whole sky that is visible from Puerto Rico. And we really know a lot about galaxies in here. But then what do we know about beyond this redshift? Very, very little. So there's one survey done with a telescope in the Netherlands, Westerbork. And then there is now this survey that we are doing. So there it goes. And we first did the pilot for this survey, which went out about halfway. That was when the VLA was being commissioned, and we could go only halfway. So now I'll tell you about what we are doing. So this is the target. This is the Cosmos field you've heard about last year if you came. It's one of the deepest observed areas on the sky. So a huge mosaic was made with the Hubble Space Telescope. And then every other telescope started observing the same region so that you could really learn about galaxy evolution. And so we are now doing that with the Very Large Array. So this is the area that we are observing with the VLA. It's just one pointing, but there's all these other data available. So it's really easy to learn something because we can correlate it to the other data. And so I just want to say this is technical details, but the reason why this has become possible is because the upgraded VLA, it's basically a new instrument. It's 10 times better in every respect than it was when it was built in the 80s, because they completely replaced the electronics. And so what for spectral line is important is that all of a sudden you can probe in one go an enormous velocity range. Which, so you could, since these neutron hydrogen lines are actually faint, so if you want to observe a neutron hydrogen line that's very far away, you have to observe for about 1,000 hours. And you cannot write a proposal to say, I want to observe this galaxy for 1,000 hours. Please give me the time. They wouldn't do that. But now we could say, in these 1,000 hours, we don't only observe this galaxy that is at a redshift of 0.5, but we detect also all the galaxies at lower redshifts. So we are observing a cone. And that is the VLA is right now the only instrument that can do that. So that is the great strength of why this is now possible. Okay, so we started out by a pilot while the VLA was being commissioned. I was rescuer in Socorro. So this was one pointing in a cosmos field. We did only half the redshift range, and we designed it so that we should be able to detect the most redshift galaxies that we know locally. So we said we need 60 hours for that. Then at least we know that things are working and we can detect this. And of course we hope that things evolve and that there are more gas-rich galaxies. So that's how we designed it. And this is what we found. So things were really working. And what you see here is the distribution in redshift space in the cone of the optically known galaxies. That is the gray points. And then red are the galaxies that were detected in 60 hours. So you see that we detect galaxies over the whole redshift range. And here you see examples of the morphology. It's actually really, really cute. Here is a very low density area. It's a void. And what do you see? A tiny galaxy with a ridiculously large neutral hydrogen envelope that it looks very disturbed, just like what we found before. If you go to higher redshifts, for example, here you see this wall at a redshift of 0.12, and you see some merging galaxies. Here you see groups of galaxies, and this is the highest redshift detection that looks like a bit strange morphology. But the important thing was we can do it, right? So we detected these galaxies, so then it was time to propose for a real deep field. And so the main challenge in this work was radio frequency interference, and I'm going to tell you something about that. And computing, we get a lot of data, and that's a big problem. Okay, so the plan for Chiles. This was another plan, so I told you I'm collaborating with all these people at the different SKA Pathfinders. And so there's people in Australia that are building a telescope, but it's not working yet, but they have a huge computer. So we said, okay, why don't we get together? We observe in Socorro, we do the calibration, and then we ship the data to Australia, where we can use their computer. So that worked fantastically well, actually. So we cover this redshift range from 0 to 0.5, and now we designed it in the same way as before. We make sure that we can, at a redshift of 0.5, detect the most gas-rich galaxies that we know locally. So that's how it was done. And so right now we are almost up to 600 hours, but I'm going to show you some results of the first 178 hours. Let's see. So we expected to detect about 300 galaxies directly in H1, so that we could make images over this entire, it's about a third of the age of the universe that we would looking back. And we estimated that in two very different ways, and we got the same number, which is very impressive. So just believe this is what we hope to get. But the big question was, will we be able to do this? And I must confess that I have been, as soon as we started talking about the VLA upgrade, which was in 1995, the first science discussion we had was, I said, I want to make an H1 deep field. And so everybody said, that's crazy, you won't be able to do this. At that time, there were no deep fields. The only thing that was there was the first Hubble deep field. And why did they say it's crazy to do this? This is something called radio frequency interference. So what you see here is the spectrum that you can measure at the VLA. Let me put this. This is the range, the frequency range of the pilot, and this is the frequency range of the whole survey. And so if there were no interference, no radio signals other than coming from the galaxies, this should be a straight line, right? So this should just be a straight line. And instead, you see these signals that are about 10,000 times stronger than what we are trying to observe. So this is called radio frequency interference. And so it's caused by the airport in Albuquerque, which fortunately is not, especially at night, it's much quieter, so you can deal with it. But it's also caused by satellites, by GLONASS and GPS. So could you please not use your cell phones and turn off your GPS? because then we can observe. It's one of the worst things we are dealing with. And so you can see here, and it's getting worse actually every year. So we talk about light pollution for astronomers, it's a big problem. Radio pollution is actually a huge problem, and we can't do anything about it. We can't hide, because wherever you go, you see these satellites. They are up there all the time. So that's a big problem, but so we're learning how to deal with it. So what you see here is the range that is really, really bad. It's from about 1100 to 1300 megahertz, and then a higher frequency is not where we observe. So it's cell phones, GPS. Okay, so I'll just tell you a little bit about the computing. It has been really interesting. And actually, I think now maybe one of the most interesting things that happened was, as we said, we first collaborated with the Australians. So the next thing that happened was that Amazon contacted us and said, we are looking for a prototype to demonstrate that Amazon can do basic science on the cloud. So they said, can we use your data? So this was another example where we got all the computing time we wanted for free on Amazon. We are still making computations on Amazon for free. I'm sure it will not last forever, but it is an amazing thing. I can tell you lots of interesting stories about the experience. So that's one of the things that happened. We have to develop lots of new algorithms, and we have to learn how to deal with the RFI. It's very challenging. But despite all that, we are making real progress. So now I'll show you first a plot, which is for me the most exciting plot of this talk, but I'm sure for none of you it makes any sense. It's a plot we just made. This is the noise in the cube that we made in the pilot. And so if you are an astronomer, you should be really impressed by the fact that it's over this huge range. It's actually most of it we can integrate down to the noise. So it's about 0.2 millijanskys, and there's a few places where there is just too much RFI and the noise goes up. So now we finally managed to make this gigantic cube, it's 31,000 channels, of 180 hours of data, and it's drawn on the same scale. So you see here the same copies, and then we have now also all this data here going to redshift 0.5. And the vertical scale, unfortunately, is a bit different here. So this is 0.2 in millijansky, and this is the log of microjansky. So to get 0.1 here, which is there, would be 2 here. So what you see is that the noise actually goes down. So we can integrate down to the theoretical noise over actually quite a large range. And if you are really fascinated by all this, then you can say, well, this is interesting. Some of the RFI is just always there. We keep seeing it. This one we see there. But this thing has really almost disappeared, which we don't know why that is, but it's much less. This is still there. And then the really good thing, and that is again for the astronomers here, the excellent thing is that actually below 1100 megahertz, it gets much better. So we get actually very good data here again. Right? It's a little bit more noisy than this, but that is because of the system temperature. So it's really good. So anybody who is designing NG-VLA should consider going down to at least 900 megahertz or maybe even 800 megahertz. The VLA could do an excellent job, and in this range, which is astronomically the most interesting range, the performance will be better again. This is something, keep that in mind. Okay, so now I'll show you some results. Just first a comparison of galaxies observed in the pilot for 60 hours and then observed for 180 hours. They grow in size in the neutral hydrogen, which says that for nearby galaxies, surface brightness sensitivity is really important. But so we thought, well, okay, we have only 180 hours, but can we detect galaxies at a higher redshift? And so what we did was, that I show in the next plot, we took all the spectra for all the galaxies in this ball at 0.12 and all the galaxies in this ball at 0.37, and we can compare the mean, right? So you don't detect them individually, but if you add them all up, you get a mean value of the gas in these galaxies. And here it is. So this is scientific result. This will be our next paper. At a redshift of 0.12, this is the stacked signal. The mean neutral hydrogen mass is 2 times 10 to the 9, 1.8 times 10 to the 9. At 0.37, we get a whopping signal. It's 3 times 10 to the 9. So if you're a real optimist, you say, wow, we are seeing that the hydrogen content increases with redshift. This is another thing we wanted to see, but this is the first time this has actually been done. Nobody has ever observed at this redshift in H1. So that's already very, very interesting. And now we come to the biggest result so far, which we have already published. So this was Jimena Fernandez, who graduated last year. She basically did this. So she had this cube close to a redshift 0.37, and she said, I want to detect something. So she just started searching through it, and she found this galaxy. And here you see the neutral hydrogen. And so we said, wow, that looks a bit weird, very interesting. Is it real? So once he found that, Hans and Jim from UMass said, okay, let me look for a CO. And he went to the Large Millimeter Telescope in Mexico and searched for CO, and it was a piece of cake. It has a lot of CO. So he immediately got the gas at the same redshift, and sort of then we believed our H1 because of him, and he believed his CO because of us. It's a really great detection. So this is one of the most gas-rich galaxies we know about, certainly in the local universe. It's not quite the local anymore. It's pretty high redshift now. It's so it has 3 times 10 to the 10 solar masses in H1, and in molecular gas there's some uncertainties. It ranges from almost 2 times 10 to the 10 to 10 to the 11. It's really, really gas-rich. Okay, so why is this interesting? So this galaxy is forming stars like crazy. It's what is called a luminous infrared galaxy. But what is most interesting, it is really asymmetric. It has a big bar. And so if you look at the gas, you see that not only is there this extended envelope, but in the disk, it's actually really totally unusually asymmetric. So the gas does not peak in the center of the galaxy. It peaks somewhere here near this disk where there's clumps of star formation. So that's interesting. Now you can wonder, is the H1 gas unique? And the answer is no. The most gas-rich galaxies in the universe, in the local universe, have about the same amount. But if you look at the CO, which is an indication for the molecular gas, it is one of the most gas-rich galaxies we actually know about. And we only know these gas-rich galaxies at much higher redshift. So here what you see is stellar mass, and here you see the CO luminosity, and this is our galaxy. And so these are known systems, and they all have less. So this galaxy is pretty unique, actually, in the amount of molecular gas it has. And what is even more interesting, you can look at the star formation rate per stellar mass and compare it to galaxies nearby who follow a pretty tight relation. It's called the main sequence. Or you can look at galaxies further away at redshifts actually larger than 1. So this is the galaxies we know nearby. Here is our galaxy. It's way off. It forms stars way too rapidly. If we look at larger redshifts, it falls bang on. So it looks like we are finding a galaxy that it's unusually gas-rich, it's asymmetric. The H1 is totally disturbed in the disk inside the galaxy. So we think this might be possible evidence for inflow. From the CO, we actually find evidence for outflow. So there is something happening in this galaxy, and we're now following it up with ALMA, which will be very exciting. So this is, it's a fantastic result, just the first result of this survey. And so these results indicate that in the survey we will be able to see how the gas affect the galaxy evolution, right? So we will be looking back to back 1/3 of the age of the universe. That's not nothing. It's a very large span of time. And so we will be able to see the morphology of the gas with respect to the galaxies, and we will be seeing what the galaxies do and what the gas does, how they evolve. So now I'll tell you in 2 seconds what the future will bring. So I told you there's these prototypes that's being built for the square kilometer array. People are building a telescope in South Africa. It's called Meerkat. It's almost ready. And they're building another prototype in Australia, which is called SCAP. In the Netherlands, they're also building a telescope. So there's 3 telescopes. They are all about to start taking data, which is very exciting. So they're not as good as the VLA, and they're very different. They have a very wide field of view, so they're good survey telescopes. But it might not go as deep. But so this will now, for example, the telescope in the Netherlands and in Australia, once they start imaging, they will do about 300 galaxies every day for the entire sky. That will be amazing. So then we will really learn something about galaxy evolution and gas. And so this is a picture of the square kilometer, which hasn't been built yet, but it will. So this will become operational in 10 to 15 years. So now I want to finish with what happens if you go to these prototypes. So I'm going everywhere because I think it's very interesting. So I went to South Africa, where they are going to build the SKA in the Karoo Desert. And so what do you think when you go there? Well, of course, this looks very much like Socorro. It's sort of desert. And it seems all the same like what you see in New Mexico. You drive forever, you don't see much. But then you look and you say, what is this? So who's been there? You know what this is. This is an amazing phenomenon. So this actually is a bird nest. And it's not for one bird, but it is for hundreds of birds. It's like a beehive. So they start out with a few birds, and then they just keep growing the nest. And in the end, you have hundreds and hundreds of birds. It's called the sociable weaver. So that's it. Okay.